So students, it seems that I'm having some issue with the Apple Pencil. I'm trying to get it connected. Yeah, it should pair now. Okay, so I think we are all set. So you should be able to see my screen. Just one yes will do.
Yes, sir.
Yes.
Okay, so the class protocol would be the following. Like at regular intervals, I'll stop and ask you for doubts. In the middle, if you have doubts, please raise your hands. Okay, so rather than unmuting ourselves and all talking, it is a better idea to um, have you yourself raise your hand, and then I'll take a note of it. Anyway, I'll take a note after every, say, 15-20 minutes. And if even after that I'm not taking a note, then maybe you can interrupt me. Okay, so let's go like that. Okay, so formally starting the course. So in the first set of lectures, we will be talking mostly about designing of efficient algorithms. Now, in the course of this topic, we will come across various terminologies and associated with them various definitions, and associated with even those a lot of mathematical notations. So this is something that you will require in all the forwarding chapters. So in all the forwarding topics that you will be learning, you will need to, estimate the efficiency somehow of the algorithms that you design. Okay, so that's why this chapter is kind of connected to all the other chapters that you will be looking forward, that will be looking into the other topics in the course. Okay, so we will start using a few definitions. Okay, so we will start the whole setup using getting ourselves introduced to a few definitions. Okay, so some of them will take you back to your school days, but then you will see that it's not always very easy, and we fumble while defining certain very simple terms. For instance, this term. So what do you mean by a problem? Okay, so I guess many of you will have your own answers, but like for all practical purposes, we can assume that this is a question that we seek an answer for. Okay, so this is kind of a roughly a formal definition of what is a problem. Okay, now typical examples of problems you have already come across in your programming and data structure course. Something like, say, sort a list of S rather, let's say, let's write it this way. Sort a list S of n elements in non-increasing order. Okay, so this is a typical example of a problem. Another similar example could be determine whether the number x is in the list S of n numbers. Okay, so these are some examples of problems. Okay, so and like most of these problems you are already familiar with, like the first one corresponds to the sorting problem, the second one corresponds to a sequential search problem. Now if I give you this problem, can you immediately go ahead and solve the problem? What is your take on this? You can use the chat box or you can unmute and answer, but not all together. What do you think? If I give you this problem statement, uh, like, is it possible for you to immediately solve it?
Sir, we need to know if it is sorted or not.
Sir,
Is
we
that
need
the first? Yeah, the second person. Yeah, go ahead. What
Sir,
were you wanting to say?
we need to know the list, sir.
You need
And
to know the list. Okay, and what else do you need?
X.
X. Okay, very good. So, and do you know what are these called?
Data.
No. In terms of problems.
Input.
Something,
Parameters.
something, yes, more specific to the mathematical notions. So, a problem, always remember this, a problem, these terms are actually something which takes us a long way. A problem has a set of unknown variables. These variables are typically called the parameters. Okay, the parameters of the problem. Now, suppose I have given you the parameters. So here in the first problem, the parameters are S and N. So let's call this 1, let's call this 2. In the second problem, there are 3 parameters. Okay, so these are called the parameters of a problem. Now, a problem with parameters specified is called? Anyone knows what is this called? Any idea?
Sir, instance of a problem.
Very good. Is an instance of a problem. Okay. A solution is the answer for a specific instance of a problem. Okay, so in algorithmic terms, a solution is an answer to the instance of a problem, not a problem. Okay, so you don't solve a problem, you solve for the instance of a problem. So this is something that we need to be careful about. Okay, now comes with all these three things. So why did we introduce ourselves to these things? Problem, solution, instance, so many things, because we wanted to come to the formal definition of an algorithm. So what is an algorithm? An is a step-by-step procedure to solve what?
All instances of a problem.
Very good. Each and every instance of a problem. Okay, so this is what is an algorithm. I hope the handwriting is legible, right? It's okay, you can understand at least.
Yes, sir.
Yes, sir.
Okay, so now we will introduce ourselves to a few example algorithms which you already know about. So the styling of the code is very similar to C, and there are like a few exceptions which I will discuss like whenever we encounter them. Okay. So the first algorithm that we write for this lecture, and of course also for this class, let's call it algorithm 1, which is about sequential search. So whenever you write an algorithm, there are a few things that you need to take care about. Okay, typically a good way, so I'm not telling that this is like one of the ways that you need to follow, but a good way of writing an algorithm is as follows. You first specify the problem statement. So here the problem statement is the key X present in the array S of n keys? Okay, that is my problem statement. Now you write down the input. I'm not sure if you have seen some scientific papers, but if you get a chance to see them, just go and look for them, and you will see that scientists typically follow this kind of a prescription to write their algorithm. They first state the problem, then they state the input, then they state the desired output, and then they start writing the algorithm, so that the reader is already, like, seasoned about what exactly the algorithm is trying to do. So this is a good way of writing the algorithm. So basically, inputs, as you can understand, are the parameters of the problem. Here in this case, a positive integer n, an array s indexed from 1 to n and a key x. So these are your inputs. Desired output, location, which is the location of x in S, 0 if x is not in S. So typically in a C style program, you start your array indices from 0. But here, unless and until it is mentioned, I mention it explicitly, we will always assume that we are starting the indexing from 1. I mean, without any loss of generality. So now the C style you have n, say it's an integer array, you have the search key, so the last one, index ampersand, is a index pointer. Since we are directly dealing with pointers, so we are not returning location value. Okay, we are setting the variable directly here. So this is a typical example of sequential search, and I guess you know better than me about this type of uh, like this type of algorithmic methods to identify. So we'll write a few more examples of algorithms, because this.
Audible in the...
Hello.
Yes, sir. Your voice broke in middle.
Yeah, that may be because of the internet. So, how long have I been audible?
You are audible, sir.
Yeah. Okay. So what I was trying to say is that like this is a typical example of a sequential search algorithm. So you know better than me how to write a code like this. Only thing here to note is that the location, since it's a pointer variable, so we are not returning it. We are setting it here itself. So it's a call by reference.
Sir, what are you writing here? Index ampersand location.
Yeah, that's what I said. I don't know whether I was audible at that time or not. So this is like you are treating it as a pointer. Okay, so this is a call by reference. That's why, see, it's a void. You don't return.
So sir, we should write int star location.
Yeah, so this is no. So that's what. So as I said, it's C style, but not exactly C. The protocol that I'm following is that it's not actually fully C, mostly C style. So here, like if I am writing something like this, so there is a special data type index. Okay, there is a special data type index that we are imagining, and this is an index pointer. Okay, this is not fully C, very close to C.
Okay, sir.
Okay, so now we will write a few other examples of such algorithms, most of which you know to code very well, but we will still write because we will have to do efficiency analysis later, and we will take these examples as like typical guinea pig cases for our efficiency analysis. So let's call the next algorithm algorithm 2. And this is about exchange sort. Problem, sort n keys in non-decreasing order. Input positive integer n array of s keys indexed from 1 to n. Outputs the array is containing the keys in non-decreasing order. So you also know this program fragment. Possibly you have done at least one variant of this in your previous labs. You follow this algorithm, right? Extend sort. It's very easy. What are we trying to do here? Especially this step. Let us only concentrate on this step, which is most important. What is being done here?
So if the right side is smaller, then we just exchange it.
Yeah, exactly. If the right side is smaller, so your motive here is always to bring the minimum most, the current minimum most to the left hand side, right? That's what we are doing.
Sir, I guess we are taking the maximum to the right.
Yeah,
Okay,
so
right.
that's what I'm telling. That's what I'm telling. We are taking the minimum most to the left. Another problem, I think this one also you have done.
Sir,
Sir,
Huh.
am I audible, sir?
Yes, you are.
Sir, sir, scroll down, sir. I have doubt in sir. Sir, you have done, sir, minimum to sir left side, na sir?
Yes.
Sir, in question, sir, we have to add, sir, decreasing order, na sir? So, sir, maximum to sir left side.
We said non-decreasing order.
Oh, sorry, sir. Thank you.
Sir, what does non-decreasing order means?
Very good question. So, what is the difference between non-decreasing order and increasing order? Who can tell me?
Sir, there can be
Sir,
equal
equal.
terms in there.
Very good. So,
Yes, sir.
so your friend, so whoever asked me the question, is this clear or should I still take this question up?
Sir, I mean, any random thing can also be non-decreasing order, I meant, sir.
Random thing means?
Like 1, 3, 2, 7, randomly placed. It is also non-decreasing order, also not increasing order.
No, these two, you understand the difference between these two?
Yes, sir.
So the difference is, like in non-decreasing order, the repetition of a number is allowed. In increasing order, in strictly increasing order, the repetition of a number is not allowed. Am I making sense?
Yes, sir. But what I meant was, if we take 4 numbers, like
Yes.
and the order of those 4 numbers is 4, 1, 2, 3. It is non-decreasing order, right, sir?
Yes.
Then that should also be true. Here we
No,
are.
this is not non-decreasing order. This is not non-decreasing order.
You mean every? Why is it non-decreasing order, sir?
Because it is
This
decreasing from 4 to 1. It should not decrease it in any two successive numbers. That is non-decreasing.
So the non-decreasing applies on the whole set, just like increasing order. It has to be continuously non-decreasing.
Okay.
Like you are blindly applying increasing order. So that's why the word order. What does it mean to impose an order? What does it mean to impose an order on a set? Have discrete structures courses started for you guys?
So just the
Just the
introduction class.
class.
Just the introduction. Okay, so even in your school days, what does it mean to impose an order? Can anybody tell me?
Sir, order means that every element should follow that rule.
Yes, every element should follow some sort of a relationship which actually imposes a kind of an order on them. So for instance, this is an ordered set, A less than B less than C less than D. Okay. But if you have A less than B greater than C greater than D, this is not an ordered set. Okay. You will read more about this. You will get to know much more about this when like there will be discussions in your discrete structures. You will read about binary relations, and when the teacher will talk about the total order, partial order, etc. So you will also come to know about different types of orders. But for the time being, order is something that gets applied to the entire set of elements. So the person who asked me the question, is this clear to you? So order means always order.
Yes, sir.
It imposes, the rule is imposed on all the elements in the set. Okay, the third one. Now this is, the algorithm is for matrix multiplication.
Sir, you are not audible.
Yes,
Oh, okay.
I'm not speaking. I'm just writing. Okay. And the output. So this is my problem statement. Now, what was the formula for the ij entry?
Sir, ith row of A is
Of
multiplied
C,
with jth
I,
column of.
yeah, ijth entry of C. Let's call it Cij. Okay. Ijth entry of C is Cij. Now, how do I express Cij in terms of Aij and Bij? This should be
AIK into BKJ.
Aik into Bkj,
Yes.
right? For k equals 1 to n, and similarly there is also the same constraint on I and j, right? School days. Okay, so now given this, we can very easily write the algorithm.
Excuse me, sir.
Yes.
Sir, is it not necessary to mention the second dimension in the 2D matrices in the argument?
So don't think of this to be exact copy of C. So this is an algorithm that we are writing. Okay. Don't confuse it with C. Many of these such things you will see that is unmentioned or goes like unmentioned. Okay. So those are like, you can assume that those things are like taken care of the underlying program construct. So we are writing algorithms. We are not writing exact C programs. So that's the difference between your theory classes and the lab classes. As long as the idea is permeated, it's all fine. We will soon see like why we are writing this. So these algorithms are not something that, you know, we are writing to just solve a problem. There are other things that we are wanting to do by writing these algorithms. Okay, so now we will talk about two problems which will give you kind of an idea of the necessity to design efficient algorithms. Okay, so this is something that like kind of serves as a motivation as to why one should design efficient algorithms. So we will question like how if inefficient an algorithm could be, and from there we would try to motivate ourselves to go for the design and development of efficient algorithms. Okay, so in order to do this, the first algorithm that we will write, this is again known to you. Same as earlier. So I guess all of you know how to write this code. Like even if I don't write, you can write it yourself. Okay, so this is how you go about doing a binary search. So I guess you all well remember what is happening. So you go to the middle of the array and then you ascertain whether the key is on the left hand side of the array or on the right hand side of the array. Accordingly, you discard one of the parts of the array and you continue searching on the other part. And you keep on doing this until and unless the element is found in the array or no such element is found. Okay. So you do this till that point, and like if you don't find it, you return 0. Otherwise, you return the exact location. Okay. So we have set location value to 0. Okay. So now we will see like the factor of efficiency that we were talking about by taking this algorithm, that is algorithm 4 and algorithm 1, which was the sequential search, and trying to compare them. So we will have a break of 5 minutes, and at 12 sharp, we will start off with the second half of the class. So you can like go have some refreshments, whatever. So we'll resume after 5 minutes. We'll start at 12.
Excuse me, sir.
Sir,
Yes.
Sir, can you please leave the notes open, sir, for our reference?
Yeah, I'll just mute myself and I'll leave the notes too.
Thank you, sir.
Sir, I have a doubt.
We will come back from the break and then we'll take up your doubt.
Sure.
Okay, so we can resume. Yeah, somebody had a doubt.
Sir,
Yes.
sir, some of them has written that out in the chat box.
Okay, let's go back and look at the chat box. Okay, so yeah, so for instance, I think many of you have written the a question about key. So for the time being, assume that key is a set of integers. So it is an integer array consisting of a set of integers. So that's what we, in most of the cases, we refer to key as some sort of data, okay, which has like a specific data type. But for the time being, you can assume that key is simply an integer. Okay. So, but key can be string, key can be characters, etc. But for all practical purposes and without any loss of generality, let us assume that key is simply some integer.
And sir, in finding mid, you took low plus high by 2, and is the outer one a ceiling function or a floor function?
What do you think?
It shall be floor function.
And what have we done?
No, sir, I didn't get the representation. I mean, the
Oh,
way you presented.
oh, so what is this? This is ceiling, and this is floor.
Okay, sir.
Any other doubts or queries?
Sir, in this function itself, sir, what is ceiling and floor function?
What is?
Ceiling and floor function.
What is ceiling and floor function? So you have to go back to your mathematics days. Okay, so this is very difficult to take up in this course. Okay, so basically, like if it is a non-integer number, because as you understand that the index has to be an integer number. So this is, since this could be potentially a non-integer number, so therefore floor and ceiling are two different mechanisms to change a non-integer number to its nearest integer number. Okay.
Sir, is it
Yes.
something like greatest integer function and least integer function?
So haven't you gone through floor and ceiling in your mathematics in class 2? So suppose if it is 5.5, okay, and you are asked to do a floor of this, it will return you 5.
Okay, sir, understood.
Okay, so now like we are trying to compare between algorithm 1 and algorithm 4 in terms of their efficiency. So for any of these algorithms, can you tell me like what is the worst number of times? Okay, let us talk about algorithm 1 first of all. When will algorithm 1 need to do hardest work, hardest amount of work?
When the element is at last position.
When the element
Or
is
it
at the
is
last.
not, or it is not
Yes,
present.
yes. When the element is at the last position of the array or not in the array itself. What about algorithm 4?
When element is not present.
Element not present. Anything else?
Or the first element, or the element is the first element, the key.
First element, that will that hardest amount of work.
No, not the. Maybe the extremes.
Middle.
Towards the extreme.
No, this is just a little more simplification of this first point here. See, you are forgetting. You are forgetting something. For algorithm 4 to work, S has to have some form.
Sorted.
So there is a yeah. So S has to be sorted. So therefore, if the algorithm 1 has to do the hardest work, sorry, algorithm 4 has to do the hardest work, what should be the nature of X? Either X is not inside the array at all, or
It isn't.
Array is not sorted.
no.
It is
Array
in
is
decreasing
sorted.
order.
It is in non-decreasing order. Array is sorted. So it is either not
All the
present
elements are
or
equal.
no.
Sir, or the x is at extremes.
What does that mean?
It's either the minimum or the maximum.
X is the largest element in the array, or X is equal to, let us write.
Sir,
Yes.
sir, will we consider the time complexity of sorting here?
We are not coming to any complexity analysis so far. We have
Okay,
not
sir.
even talked about that. Please let us go
Yes,
along
sir.
with the class, okay? Because there are many friends of yours who are probably seeing this kind of concepts for the first time. I know many of you are already much ahead of the lectures, but this is a humble
Mm,
request
No, sir.
that
Like, sir, the array could be in the decreasing order, and then we have to sort it again and then find. So it would be like,
no, if the array is in one of the orders, you don't need to sort it anymore.
okay, sir. Thank you, sir.
Yes, sir. We can just change the sign of greater than and less than.
No, you can do even easier things. You can have one, I can give you one additional variable and you can use that to do whatever you want. Just
So what
one
do you?
additional. Huh?
So what do you mean by work? Like what all comes into work? All the additions, subtractions, comparisons, or else
Very
all
good.
the
Very good
assignment.
question. Very good question. We'll come to this. I just wanted to have your understanding or your notion about work. We will specifically come to what work means. Okay, and this is what all this chapter is about. What do we mean by an algorithm doing work? Okay, so
Sir,
The algorithm, the smallest element can also be the worst case, right?
smallest element will be the worst case.
Yes, sir.
Okay, agreed. Agreed. Okay. So now suppose I write the numbers for you. Let's say we enumerate the array elements. So in the first call, immediately after the first call, where will be your mid? Suppose X is not in the array or X is the largest element in the array. Where will be your mid?
16.
16. Okay. After the first call. Then after the second call,
24.
24. So it seems you are all with me. After the third call, it will be at 28. Then it will be at 30. And then finally it will be at 31. So how many calls? If you look carefully, the number of calls is 6, which is, somebody is unmuted. So the number of calls is 6, which is okay. So it is logarithmic in the number of inputs or the size of the array S. Okay, so it's roughly logarithmic. So there is some additional constant. So it is roughly logarithmic in the number of elements present in the array. So general case.
Excuse me, sir.
Yes.
So here, if X was the largest, then there would be 6 calls. But if S was in 31 position, at that time it will also be 6 calls.
Yeah, okay, fine.
I think
What?
there are many positions for which there will be 6 calls. Like X is not the only one.
We just took the one of the extreme cases that is possible. So where are the other cases? As we say, in the first, if X was in the first position also, it will be 6 calls.
Yes.
Okay. Yeah, and I agreed to that. I already agreed to that.
So I am asking, how can we determine all the positions?
That's a homework. What are the other cases where you think this is possible?
Like in 3129,
In 3129, there will be how many calls?
6 calls.
Why?
Because from the fifth call, we will see that 29 is less than the 31 position.
Yes. Then what will you do? It will return location equals 0 immediately.
No, the 21 is not that.
Every case it will be less than 6 calls, except
In
for
the
the two extremes. Except for the two
Okay.
extremes, every case it will be less than 6 calls.
Okay,
Okay. Now we will see another very efficient example, very inefficient example. So, and this is like an epitome of inefficiency. But you will see that this is so low hanging that we always tend to use this form of the solution, and typically we use this form of the solution more than the other form of the solution. We will talk about both the forms of the solution, but now we will see one by one, and then like you will probably appreciate with me that in general, like if you are not well aware of the efficiency or well concerned about the efficiency of an algorithm, the first variant that we will look into is something that people typically are adopting when solving this problem. Okay, so without any further ado, let's go to the next problem. This is our algorithm 5. Remember this series?
Yes, Fibonacci series.
Yeah, this is the Fibonacci series. Okay, for a Fibonacci series, we know so the moment we are asked to, write an algorithm to generate the numbers in the Fibonacci series, like our programming prowess actually like drives us to write this version. So the problem here, as earlier, I hope you know what is a non-negative integer. So this is all integers inclusive of 0.
Whole numbers.
Yes, whole numbers. Yeah. So the moment you are given this kind of a problem, you know, our smart like inner intent immediately drives us to write something like this. See, I'm so restless that I'm making silly mistakes. So this is a recursive version, right? A recursive version of generating Fibonacci sequence. Now, yeah, people will probably agree that if I write this kind of a code snippet, this is correct. And of course, like probably I will also be considered smart, quote unquote smart. But then a software engineer or a design engineer will not really consider me very smart. Can you tell me why?
You're doing repeated work.
There is efficient way of
Yes.
doing it.
Yeah. So this code is an example of extreme inefficiency. So, and this can be understood by drawing something called the recursion tree. I don't know whether this was done in your PDS theory or lab.
No, sir.
Okay. So we will do it here. So suppose I start my call with fib5. Okay. So what will happen? This will initiate 2 calls, right?
Yes, sir. 4 and 3.
Fib3 and fib4. Fine. Now fib3 will initiate fib1 and fib2, and fib2 will initiate fib0 and fib1. I guess you have already started seeing the problem. Fib4
Yes.
will initiate fib2 and fib3. Fib2 will initiate fib0 and fib1. Fib3 will initiate fib1 and fib2. And fib2 will initiate fib0 and fib1. So you see, in order to compute fib5, we have called fib2 once, twice, thrice. 3 times we have called fib2. We have called fib3 2 times. We have called fib1 1, 2, 3, 4, 5 times. And we have called fib0 1, 2, 3 times. Okay. So you are calling, in order to do a computation, you are repeatedly calling the same function multiple times and their outputs are all same, right? Okay, so that means it's pointless to call them multiple times, but you are doing so. Okay, so do you get this? So
Yes,
why
sir.
I am calling this inefficient? So this is extremely inefficient. Okay, so now let us try to find out how inefficient, mathematically try to quantify how much inefficient this algorithm is. Okay, so this is an answer to one of you who was asking me the question like, how do we measure the work done? This is the first answer. I'll give you a more formal answer soon, but this is, and you can take this one as an initial answer. So in this particular example, one way to identify the work done could be to check for the number of terms computed. When you wish to find a particular number in the Fibonacci sequence. Okay, so let us try to do this. Let's make a table first. Starting from 2, can you see any pattern?
Yes, sir, the number of terms for any number can be given by the sum of previous two values plus 1.
That though is the kind of a corollary of the Fibonacci sequence formula. Anything else do you see, like
Number of calls are growing exponentially.
exponentially to fine, but any relationship?
So 2 raised to power n minus 1 minus 1.
So now you are coming to the answer directly. I am asking for a simple observation. You are just coming to the direct answer. So suppose you have to, like in the footing of a teacher, you have to help your friends also to understand. What will you do then?
Tn minus 1 plus Tn minus plus 1 plus 1.
Okay. Any other thing? Anything else that comes plain from, suppose if I give you this table, you don't know anything about Fibonacci numbers. I give you a few more numbers in this table. As a data scientist, so you know data science has become very, very hot. Can you find some pattern?
The difference
The
increases.
numbers keep increasing by
The
1, 4,
increase
8.
also.
Okay. Anything else?
Sir, if you subtract 6 means 25 from 15, then it gives twice the number of calls in the third one. It is true for every answer.
Sir, the difference
Closer.
Fibonacci
Closer. Closer. Okay.
Sir, the difference is forming a similar pattern of the one which we use for the Fibonacci series.
That is so fine. But suppose you don't know about, I give this table to a school child or somebody who does not have any idea about Fibonacci series.
Sir, the difference is twice of the Fibonacci series.
Okay. Okay. So can I say,
Ratios,
can I?
the ratios seem to be oscillating. Like you see 5 by 3, it's somewhere about 2. Then it goes below to 1.8, and then after that again it's 5 by 3. So these seem to be oscillating between and like will probably converge, I guess.
Okay. So can I say something like this? Something like a way in layman's terms.
Sir,
Yes.
difference of difference is going in powers of 2.
Okay. Okay. Let's put this on a halt and let me try to say something very, very simple and see like if this makes any sense to you. So if I say that the number of terms more than doubles as you increase the value of n by 1. Is this true?
No.
For 5 to 9.
Even for 15 to 25, it is not.
Not so. Okay. So then now if I say that, see, I'm trying to incrementally make this thing so that you remember. Now suppose I give a question mark here. And I say that I claim that there is a pattern out there. Can you tell me?
It's doubles minus the Fibonacci sequence.
Increase n by 2.
Increase n by? Yeah, you are correct. Come again?
2 by 2.
By 2. Okay. And is this okay with everybody else? Do you see this? Your friend has already seen this. Okay, fine. So let's say now that Tn be the number of terms in the recursion tree for n. Let us say that Tn be the number of terms in the recursion tree for n. Therefore, I can say that Tn should be greater than what? Given the previous premise that we have just now written.
Tn minus 2.
IT of n minus 2.
2 into
Tn minus 2.
Tn minus 2. Okay. Am I correct? Can I write this?
Yes, sir. Yes, sir.
How many such terms?
n by 2 minus
2 to the power n by n by 2 terms. Yes.
N by 2 terms. Okay. And we know T0 is 1, right? So this means Tn is greater than 2 to the n by 2. Any constraint?
N greater than equal to 2.
Very good. So just by observation, like a data scientist, we have come to some interesting connection between the number of terms and the number itself. Okay, the number of terms in the Fibonacci sequence and the number of terms to be computed to get the number at position n, okay, and the number itself. Now, if I tell you that prove this, prove this inequality using some proof technique. What are some of the proof techniques that you remember?
Induction.
Induction. Okay. Very good. So this will be a proof by induction. So base case, as we said, that n has to be greater than or equal to 2. So if you see T2 is how much? 3, right? That is greater than 2 to the power 2 by 2. T3 is 5, which is greater than 2 to the power 3 by 2. 2 to the power 3 by 2 is actually 2.83. So therefore, it is greater than 2 to the power 3 by 2. Okay, so the induction hypothesis. Can anyone tell me the hypothesis?
We assume Tn to be true and then prove Tn plus 1 to be true.
We assume Tn and Tn plus 1 to be true for some n greater than or equal to 2.
Okay. So what is that type of an induction called, where you want many previous terms or typically all previous terms to
Strong
hold?
induction.
Yes. So here our hypothesis will rely on the principle of so strong induction. By strong induction hypothesis, I will assume that Tm is greater than 2 to the m by 2 for m such that for all m such that m ranges between 2 and n. So this is true for all m, which is the principle of strong induction. Now the inductive step. You know from the Fibonacci sequence formula that Tn is equal to Tn minus 1 plus Tn minus 2. Okay. So Tn is greater than, given that Tn minus 1 is greater than 2 to the n minus 1 by 2 and Tn minus 2 is greater than 2 to the n minus 2 by 2, we have from these two that comes from the inductive hypothesis, we have Tn to be greater than 2 to the n minus 1 by, sorry, there is this plus 1. Why is this plus 1?
Calculating itself is also a term.
Huh?
Calculating
The ultimate term in the recursion tree is also a term that you have to compute. Is this okay with everyone? When you are computing, remember, recall that Fibonacci tree, the recursion tree. When you are computing everything, say for Fib5, so you have to also compute the last term. That is the root of the tree. And that's why that 1 is out there. So what is the trick now? What is the trick to go to that 2 to the n by 2?
2 to the power n minus 2 by 2 plus 1.
Very good, very good. 2 to the power n minus 2 by 2. This you can always write, right? Because n minus 1 is greater than n minus 2. Oops, I'm so sorry. Okay, so this gives you So you have proved okay with everyone? Any confusion, any doubt anywhere? Okay, no, seems like no.
So please
Yes.
explain what by strong induction means.
Strong induction. Okay, so strong induction you have to please look for in the in Wikipedia. There is a nice article on Wikipedia. So please go back and look into this. This will be also taught in your discrete structures. So basically, strong induction states that the inductive principle holds for all the elements that you have seen so far. Okay, so as you see here, the inductive hypothesis holds for all m less than equal to n, strictly less than equal to, so strictly less than n. Okay, so it starts from whatever value of, so in this case it starts from 2 and it holds up to any value of m. So in this case the extreme value is n minus 1. Okay, so for all these values this is true, and that is what we assume in strong induction.
Sir, I have a doubt in here. Sir, you stated that 2 into 2 to the power n minus 2 upon 2 plus 1. And then in the next step, you said that it is greater than this part. So, like, if plus 1, wouldn't that be a problem? Like, if I'm saying that x is greater than a plus 1, then how can I say x is greater than a? Yes, yes, I got it. I got it.
Okay. Okay, fine. I think you answered yourself. Okay.
Yes, I got it, sir.
Okay. So now, like, so all this was like an example of a very inefficient way of coding. What is an efficient way? Let's call this.
This comparison is also very inefficient.
Huh?
So this comparison that we are making that Tn is greater than 2 raised to power n by 2.
This is the mathematics. Okay, this is not something that you are doing in your code.
So, but it can be misleading, sir. Even for 6 also.
No, I don't understand. What do you mean by that?
If we see the T6, it is 25.
Huh?
And from here we will get that T6 is greater than 8. So 8 and 25 are very different.
Yeah, that's true. That's true. That's true. This is a
It will not help.
Huh?
It will not help much then.
What will not help? I'm not understanding.
Like to find Tn.
So basically what we are telling that this is kind of the worst that you can take. Okay. This is kind of the worst. It is going to be slightly better, but this is kind of the worst that you can take.
Okay.
So the same thing. Now the efficient version, I guess all of you know this. I am not writing problem input etc. This you can fill it up. I simply take an array. Okay, so this is an efficient version where you really don't need to recompute the terms. Okay, so anyone knows what paradigm of algorithm was the first one, and what paradigm of algorithm is the second one?
First one is recursive and second one is iterative.
These are not paradigms. You know about paradigms? We will learn about paradigms in this course.
First one was divide and conquer.
The first one was divide and conquer, and this one?
Dynamic programming.
This is dynamic programming. You will, so the next two topics that you will get to know about are the two topics that you just now mentioned. This next one, immediate next one is divide and conquer after we finish this chapter. And then the third one would be dynamic programming. Okay, so fine. So we are now in a position to understand, at least to some extent, what do we mean by efficient algorithms and what do we mean by inefficient algorithms. But then the question still remains. I remember one of you asked me in the beginning of this second period that what do you mean by this work being done? Okay, and how do I like make an estimate of how much work has been done? So this is what we will try to answer in the next 4 or 5 minutes of the lecture. Okay, so if I say that, okay, work done by the algorithm how do I measure this? Okay, so I can have different answers. CPU cycles, number of lines of code, then what else? I can think of many other things, including the programming language, etc. Okay. Now, do you think that these are good measures?
No, sir.
Why?
Because it will vary from system to system and
so
program.
This will vary from
System
machine
to
to machine. Yeah, machine to machine or system to system. Okay, machine to machine, this will vary. What about this?
Sir, it's misleading, right?
This will vary from instruction set to instruction set. This will vary from language to language. Then what?
Sir, the time it takes to execute the program.
Time it takes to execute the program. That is what is CPU cycles.
So can it be like the stack of memory that is getting in the CPU?
So that is the size. That has nothing to do with the time or the work done.
So number of operations.
Number of operations.
Which
calculation, basic calculation.
calculations? What calculations? What operations?
Assignment.
So
Increment.
we can declare some work as a standard unit and divide the time it take for the program by that time.
What is time? What is
Like
time?
our algorithm takes some time in seconds, and we can like make some like a standard. This code will run in this time, like some t seconds, and when divide every algorithm's time taken by that time.
No, that is not.
So I think the time taken depends on the computer, right? So if you take
Yes.
that away, so instead of that, talk about the growth of the time. So that will be same across computers, across CPU sets, because
No. The growth might not be same. The growth also might not be same.
Can you give an example of the growth might not be the same, sir?
Depends whether you are executing the code on a CPU or a GPU.
I mean, if you parallelize the computation across multiple cores, and then that's different.
No. There is no parallelization in GPU. It's not that you are parallelizing things.
So I don't understand the.
In GPU, you don't always parallelize things.
Yes, but still the number of operations. I mean, the time that you take still has to grow as like a function of your input, right?
No, so this is something that, so you have to divert your attention from time. So time as, so what do you mean by time? Time as in seconds, milliseconds, that time?
So not that time, instead of number of operations. So we could have that as a baseline.
Okay. So this is where, like, so if you are talking of times in seconds, milliseconds, then this will not work. So here, the time is more like a notional time. Okay. And in order to understand work done, we need to appreciate two terminologies. Basic operation. From now onward, I will call this basic op. And input size. Okay. So these are the two things that are crucial to the understanding of the work done by an algorithm. So it seems that we have already surpassed the time. So we will restart our discussion from this point onward next day. So let me know if there is any problem with the accent or the delivery or the English or the writing, whatever, like apart from the technical inputs, like let me know if there is any issue that is bothering you in the I mean, in order to follow the lectures. Okay, you can tell me now, you can write over mail.
Sir, can you please upload a screenshot of these algorithms or a PDF?
Screenshot of this algorithms means these
I mean
notes.
those
PDF. Yes, we will have it. I'll do it. As I said, I'll do it.
Okay.
Sir, I want to ask that, sir, will we get some kind of tutorials for this, for the theory part of the algo one, like for practicing?
Of course, we will share questions. Okay.
And sir,
We will
for the practical lab,
everything.
is there any...
So for the lab, we will directly practice the lab assignments of the last years in the tutorial class. And also in the tutorial class, like we will give you a bunch of say 10 to 12 questions. You can try solving them. If you can't solve some of them, you get back to us on the next tutorial day, and we will try to help you to get the solutions. It's all about more you practice, more you learn.
Okay, sir.
Sir, and what type of questions will be asked in algorithm theory? Like
What type of questions means in the exams?
Yes, sir.
So on the first day of the lectures, is it a good idea to talk about exams?
So just out of curiosity, I got.
Let us first learn. Let us appreciate the subject. See, if you start appreciating the subject, exams will typically become easy for you. That is what I feel. Start appreciating the fundamentals of the subject. When we will share questions with you, when we will do the tutorials, you will get a fair enough idea of what kind of problems you are going to face in the exams.
Okay, sir.
Any other questions?
Sir, excuse me. I had a doubt, it is not related to today's lecture. It was related to yesterday's lab. I had messaged you in Teams. Can you please help me out there?
Message?
It is not about the assignment. It is like a specific problem which I am having. I don't understand why it's happening.
Okay, so just write a mail to us. Have you written it to us?
Sir, I have messaged you, if I'm not wrong, in MS Teams.
Oh, in Teams. Okay. Why don't you send a mail to me?
Okay, sir, I'll do that.
Yeah, it's better you send also send a mail to AlgoTS. Okay, the AlgoTS group.
Okay, sir.
I think it's algo1ts@googlegroups.com.
Yes, sir.
Okay.
There is a Google group. Can we send email? Okay.
Yes,
we can also send email.
Yes, you can send email. We have kept the permission open. You can send emails. Anybody can send email. Okay.
Sir, thank you.
So and CC me and Pavan.
Sure, sir.
Yeah. Okay, so MS Teams many of the times, especially if it is out of the class hours, we typically don't follow. So it's best to write over emails. Okay.
Surely. Yeah.
Okay, guys. So see you on 18th for the tutorial, and then again for the class on 20th. Bye.
Thank you, sir.
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 Thank you, sir.